All right, good morning to Calculus 2. We are going to be talking about parametric equations today. And I'm going to say a couple of things about that before we start. First off, I apologize for your book. When I learned parametric equations, it was a fairly straightforward and an easier sort of a way to go about things. It's the whole thing about a tool. If you make your life easier, then you're going to be inclined to use the tool. If they present it where it's going to be very difficult, then you're inclined not to use the tool. So your book pretty much presents this in ways like, why did they do it this way? So my apologies, but here we go. So the idea behind a parametric equation is we're going to introduce an independent parameter, okay, usually t or theta, okay, and we're going to say f or x is equal to some kind of a function of t, and y is equal to some other function of t. So we're going to generate t's, and we're going to graph x's and y's because of it. So why don't we start off with an incredibly nice, easy example of this. So we'll say something like x is equal to t squared minus 2t, and y is equal to t plus 1. Okay, this is the example in your book, but it's nice just to get kind of a start with it. We'll make a little t table. Okay, so here's our t, here's our x, here is our y. Okay, so we've got t, and they just come up with some values for it, and that's all we're going to do here is just come up with some values. All right, maybe more than we need. Okay, and we're just going to plug these values in. Okay, so we have negative 2 squared minus 2 times negative 2. That's going to be 4, right? 4, and then plus 4 is equal to 8. X is equal to 8. And at the same time, negative 2 plus 1, negative 1. Okay. For the next one, value of negative 1, we're going to say negative 1 squared minus 2 minus 1. 1 plus 2 is equal to 3. Okay. And negative 1 plus 1, right, for the y is negative 1 plus 1 is 0. Okay, plug in 0, we get 0, we get 1. Okay, I can do that one. We do a 1, right, we get 1 squared minus 2 times 1, so that's just going to be 1 minus 2, negative 1 here. Okay, 1 plus 1 would be 2. Okay, I'm going to go ahead and do something here. I should have probably graphed this out this way. Okay, line paper and all. Let's see, we have 2 squared minus 2 times 2, so it's going to be 4 minus 4. We get 0 again, right? Yeah, we do. Okay, and then 2 plus 1, right? Y, t is 2, y is 2 plus 1, so 3. Okay, we have 3 squared minus 2 times 3, so it's going to be 9 minus 6 is equal to 3 here. And 3 plus 1 is 4. And then we have 4 squared minus 2 times 4, so that's 16 minus 8 is equal to 8. And 4 plus 1 is 5. Okay. Now we're just going to go ahead and graph this. Okay, so I'm going to make this a little bit bigger. Okay. Let's see, my x's go from 8 to negative 1 to 8. So, and my y's look like they're all mostly positive. All right, so let's go ahead and graph that. So we're going to do this. And here, so here's my x, here's my y. So even though we use parameter t, we're still graphing on the xy plane. Okay, t is just an independent parameter that we're going to be using. I'll show you what that does to our graph. We're just going to plot some points. Okay, so when t is negative 2, x is equal to 8, y is equal to negative 1. So we're just going to come out 5, 6, 7, 8, negative 1. Okay, that's our first point. Second one, right, x is equal to 3, y is equal to 0. So here we are, right, x is equal to 3, y is equal to 0. When t is 0, then x is 0, y is 1. Okay. 0, 1. Then we have negative 1, 2. So here's negative 1, 2. All right. Let's see here. We have 0, 3. All right. And then 3, 4. 1, 2, 3. 1, 2, 3, 4. Okay. And then we have 8. And then we are all the way up here at 5. Okay. So if I'm going to go ahead and trace this thing out, screen, okay, what's going to happen is, right, we're trying to connect the dots here. I'm trying to be a little bit careful about that. But what's happening, right, is that we're kind of going from this kind of direction here. Okay, pretend these actually line up with our thing here. Okay, you don't have to do quite so many arrows. One is probably plenty, but you can see, right, we have a parabola that's opening to the right here. All right. So that's the idea of a parametric equation, is that normally, excuse me, normally we'd have this function of y, but because we have it instead of in t, it's easier to kind of break this thing down. The real kind of cool thing about parametric equations is that you can tie these things up in knots, and it's really kind of cool to do that. All right, now you have to be a little bit careful. Okay, if you do a good, nice Google search on how to graph in TI-82, or 83, 84 rather, you'll get a really nice sort of a thing. But I'm going to go ahead and pause this for just a second so I can bring something up here. So I'm going to bring up Desmos here, and if I wanted to graph the previous example in Desmos, okay, your calculator will do just fine, by the way, for this one. Okay, so what we're going to do is we're just going to write down an ordered pair. We're going to write down, this is t squared, right, minus 2t, parentheses, okay, and it should be t plus 1. And then what do you want to do if we started at what, negative 2, and we went up to 4? Right? And you can see we pretty much got the same sort of curve that we did for the one we just did as an example. That was polynomial. That was pretty tame. There's no weird discontinuities or anything like that. You know, you can change this, right? We can, instead of negative 2, right, we could have gone to negative 3, right? Just extend it out. But wherever you need your time to go with, then we could do that. And you're going to use these a lot in physics. T is often going to be time, so we'd start with that, and we'd have like this trace of this particle looking something like that. Okay, so that's kind of nice. I was going to do another example for you, which was ordered pair. How about secant x? Oh, secant t rather, and then tangent of t. All right. Now, this one, if you put it in your calculator, it's going to be a bit harder to deal with. Okay, because there's a discontinuity here, and your calculator is going to have a tough time with this. So what if we go ahead and do something like from you know, negative pi to positive pi? Okay, kind of take a look at what's going on with that. So again, right, it's kind of a nifty little curve you can draw, and I encourage you, like, go into Desmos and mess around with a whole bunch of these things, because they really are kind of cool to play with. But you know, realize that your calculator may not be the best tool for the job in graphing these. I only have a TI-83, and mine looks it looks really crummy when I do it on a TI-83. But actually, let's see, how do you do that? If I was going to do this one on a TI-83, okay. So again, there's better videos to show this than this one. Just look for parametric equations on your calculator of choice. I'm sure there are dozens of YouTube things that'll come up for it, and now maybe this one. So what we're going to do is we're going to go to mode. Okay, we have to go down to PAR parametric. Okay, enter, and then we're going to quit. And then what we're going to do is we're going to bring up our y equals for our graph, and you can see, right, you get an x and a y here. All right, So for my x, I'm going to write down secant. I'm not going to write down secant. I'm going to write down, oops, I want delete. I want to delete everything. They don't have a secant. Remember that second function cosine, that's inverse cosine. That is not 1 over cosine. That's secant, okay? So we're going to say 1 over cosine t, all right? And then my next one, my y, is going to be tangent of t, okay? And I know they use capitals, but whatever. All right, and I think our window, right, what do you want for our t? So we're going to say, negative pi. Right? I don't know how to do this more than once. Okay, so the first time we do it, if it doesn't show you exactly what I want, like I think we're out of luck. Okay, and then I think we're going to go ahead and say graph, and that should go through and do that. So you can see, like, it kind of approximates this thing, but it's nowhere near the kind of the graph it will show. You don't really see the discontinuities in there unless I guess you zoom in real close. And even then, the calculator takes a lot of liberties with what's going on here. So when you're dealing with like anything that has discontinuities in it, both secant and tangent both have discontinuities, I don't know how much I would trust your calculator, okay? And if it's a pretty tame one, most of them are pretty tame, right? We do sines and cosines and we do polynomials. They're going to be a lot easier to deal with, okay? If we went through and did our first example, it would graph it just fine. All right, so don't be afraid of using it. Just understand that if it's got, fractions or, stuff with discontinuities, that there might be better tools out there, and yeah, to deal with it that way. Okay, so yeah, that's how to graph parametric equations. It is important, like, go through and deal with that. Right? And we can go ahead and do it. Okay, next idea. They want to eliminate parameters. Okay, so if we go through all this point of coming up with a parameter, now they want to say, how do we get rid of the parameter? So in polynomials, again, it's very straightforward, and I like how they do for this one. We'll go back to blue. All right. So x is equal to, same example, t squared minus 2t, and y is equal to t plus 1. All right. And all we're doing here is we're saying, well, t is equal to y minus 1 is equal to t. So now we have a t, so we have x is equal to y minus 1 squared minus 2 y minus 1s. And then we're just going to sort all of this out. Okay, that's all we're going to do for this. We just substitute it. So we have y squared minus 2y plus 1 is equal to 2, or minus, no, not is equal to, minus, and then we have 2y minus on minus is a plus 2, yeah? So here we have y squared minus 4y, 1 and 2 make 3, equals x, okay? And that's, that's a sideways parabola, right? It's got some intercepts there, we can go through and say, well, this is going to be y minus 3, y minus 1, solve for the intercepts and all of that. And that agrees pretty well with what we have drawn here. Okay. Like I said, the use for this is when you have to go around and tie this thing into a, you can tie this thing into a knot and overloop itself, and that's fine because it's a parametric equation, it's not a function. But that's pretty much how this works. Okay, so they give us a nice, easy example and then went from that. Then we get the trig. So let me go ahead and give you, okay, this idea. Okay, and this is a little bit more hand-wavy. So what we're going to do is we're going to graph it first. All right, so we could have a t, we could have an x, we could have a y. And I'm just going to go with real basic. Oops, I want 3 pi over 2 is what I want. And then finally I want 2 pi. We'll follow up in Desmos, but I think having some degree of being able to solve this by hand is always good. Okay, I plug in t equals 0, right? Cosine is equal, cosine 0 is 1, sine 0 is 0. Plug in pi over 2, we get 0, we get 1. Plug in pi, we get -1, 0. 3 pi over 2, we get 0, we get -1. And 2 pi again, we get 1 and 0. Okay. 1, 1, -1, -1. So in t is 0, we get x is 1, y is 0. So we're here. Then 0, 1, -1, 0, -1, 0, -1, and back to 1, 0 again. And if you thought like, well, is it really going to be as simple as this? You'd be right. It is as simple as that. It's a circle. Okay. So it's a circle with radius 1, center at the origin. So if I wanted to write this in x's and y's, it would be that. How are we going to get from here to there? Well, what we're going to do is we're going to say, well, if x is equal to cosine t, x squared must equal cosine squared t. Y equals sine t, so y squared must equal sine squared t. And then we're going to say, well, I guess we're going to have cosine squared t plus sine squared t is equal to 1. Right? That's our parametric equation here. Okay, and we're going to say x squared plus y squared is equal to 1. Okay, so that's pretty much the tool for turning this into an x and a y. So how was I supposed to know that without knowing that was the answer? You aren't. Okay, that's the deal with this, is that you aren't. That's why I show it to you, so that when you come across this, you're like, oh, okay, it's got to be this technique rather than a technique for polynomials. So if I was to go ahead and do this, right, we'd have ordered pair cosine t, oops, yep, sine t, and again, what do you want to go for? We'll go from 0. I don't know if I can do 2 pi on this. Let's go with 2 pi. Oh, look at that. They did it. Okay. Circle, radius 1, right? How do I make it bigger? How about we do a 3 here? Oh, look at that. If the coefficient, this will come in handy later. If the coefficient at the cosine is bigger than the one for the sine, we get an ellipse. I wonder if, I don't really wonder, but if we extend the other one, make the other coefficient big, then it's going to do that. So if we do both, then we go back to a circle again. Okay, so I want you to remember that if these change, we start getting ellipses, okay, rather than circles. If the coefficients are the same, we're going to stick with a circle. And again, our little arrows here, which we're not going to write on Desmos, that goes from 0 and it's going up and back around, okay? So just to give you an idea of, what this is supposed to look like, okay? Now that when you want to change it back to eliminate the parameter, you've got something to aim for, right? You've got a target to aim for. You can see we could do this. We could say this is 2 cosine t, 2 sine t, and again, we're still going to go from 0 to 2 pi, and we'll change that to red. Oops. Now it looks like a target. Okay, so you've got something to kind of aim for as you're changing your parameters. Okay, because it is grossly unfair. It's like, here's a very useful and this is a very natural technique. Now we're going to change the trig, and we are going to take that all the way from you and make it a completely unnatural thing. You kind of have to know what you're doing. Sorry, it's the way it is, though. All right, we have substitutions, right? So if we have, say you have a function you want to change into a parametric equation, okay? So you have x equals some horrible thing, y to the 4th minus 3y squared. And you would like to change this into a function of x. Like, no, not happening, okay? We're not going to do that. So, but one way to work with this thing, right, is to change it to a parametric equation, because this is a sideways vortex, which looks delightful to graph and everything, but we could say that x of t is equal to t to the fourth minus 3t squared. And then y of t is t. Like, that seems like it's cheating. It isn't. This is a very common way of turning your function, right, that it's in Cartesian coordinates, into a parametric equation. Okay, that's very common. But notice that this gives you a lot, you know, if it was a more complicated function, if I wanted to do, you know, dx by dt, dy by dt, this is much easier than dealing with maybe things that overlap and everything else. Okay, so I just want you to realize this is going to be more complicated, although still should be easier. Yeah, you don't always have to break everything into x's and y's and do that. Okay, so that's how you change it back. Okay, so let's see here. We have some homework demonstrations here. If I can find out where I put those. We'll see about that. So let me pause this for just a moment and we'll do a homework or two and I'll follow up with some more. All right, so let's go and take a look at some of your homework here. So this will be a little bit of a demonstration. So the first thing they ask you to do, well, not the first thing, but you know, for the first couple of problems, it's a couple of examples. Some of them we did. Okay, we actually did, I think, one of them. And any other one, they just kind of ask you to get familiar with this by trying the thing yourself. I think you'll be okay to do that. And this is a little bit more. If x is equal to, right, x is equal to sine of theta over 2. Remember, theta could also be it's a very common parameter is theta. Y is equal to cosine of theta over 2. We go from negative. Okay, you have to be a little bit careful with this. This is very common that they switch the x usually goes with cosine and y usually goes with sine. At least it does in physics. We like to do that opposite in calculus. This always bothered me. So if you're looking at this and like, it's confusing, why are they doing it this way? Like, I hear you. I hear you. But let's go ahead and track out a couple of problems just with these things. Before we go ahead and eliminate the Cartesian equation, let's just go ahead and do this. Okay. So what we're going to do is, okay, when theta is equal to negative pi, right? So if I plug in, right, we have sine of negative pi, okay, cosine of negative pi, then our x value, right? Our x value is -1 here. Our y value is 0. Okay. Let's go ahead with theta is negative pi over 2. So we have sine, right? Let's see. Maybe 0 would be better. Okay. But that's going to be negative pi over 4. Cosine is going to be, right, negative pi over 4. They're both in the third quadrant here. Actually, they're not going to quite be in the third quadrant but we're going to have x is negative root 2, right? Y is root 2, right? Because negative cosine is, right? Cosine is an even function, so it eats the negative. And you don't have to worry about that. Okay, how about theta is equal to 0, right? We're going to get sine of 0. So x is equal to 0. And we have our cosine of 0. So y is equal to 1. Okay. And then we'll go up to theta is equal to pi. So we have sine pi over 2 rather. So it's still 1. Cosine pi over 2 is 0. Okay, because remember it's theta over 2. Okay. Now to graph this thing, okay, I should have been a little bit neater about making all of this up. Okay, so when theta is negative pi, we start off at the point, right? Negative 1, 0. Okay. So we're here. Okay, theta went to pi over 2, negative pi over 2. So we're at negative, right? My x value is negative pi over 2. Y value is square root of 2 over 2. So that's going to be in here somewhere. All right, so here we are. All right. When theta is equal to 0, we get 0 for x and 1 for y. So it looks like we're doing that. And I'm just putting the arrows in here so I have an idea of which direction this is going in. And then theta equals pi, we get, right, x is 1, y is 0. All right. So there's our function that we have. Okay, if I'm looking at my piece here, right? See, told you the arrows were going to be important. Okay, then we can go ahead and type in and say, okay, I think it's this one. Okay, and then it says eliminate the parameter to find the Cartesian of the plane. So again, what we're going to do is we're just going to note, and we're going to say x was equal to sine of pi over 2, theta over 2. Y was equal to cosine of theta over 2. So we note that x squared is equal to sine squared of theta over 2. You can call that any angle you want, right? Y squared is equal to cosine squared of any angle you want. So we still end up with sine squared a plus cosine squared a. It's just that in this case, our a, right, goes from negative pi to negative pi to a to positive pi. This was theta over 2, right? That was my a. Negative pi to pi. So we have negative 2 pi theta to positive pi 2 pi, because we're just multiplying by the pi's, and we end up with sine squared. Oh, x squared plus y squared is equal to 1. I don't. I would like to keep this as a upper part of this thing, right? So we might say, you know, let's put a domain for x in here, negative 1 to positive 1. But y, again, I'm using the picture, right, to guide what I want here. So we'll put in that for my x and my y, because that's going to match my picture. Okay. So that's not really going to help. Okay, so there we go. Right. Go back to our homework, take a look at that. So we could type in x squared plus y squared equals 1, but we would definitely start from x equals negative 1 to positive 1, kind of a thing. All right, consider the following. We're going to eliminate the parameter and see what we see. All right. Oops, I don't want that one. I want this one. So here we have x is equal to e to the t, and y is equal to e to the negative 5t. Okay. Now there's a couple of ways we could do this. Some of you guys have to work on your rules of logarithms and rules of exponents. But right, if we have an a to the b to the c, that's equal to a to the bc, right? So since we have something that's multiplied, I can mark it in this direction. Okay. So since e to the t is equal to x, we have y is equal to x to the negative 5. All right. So this is 1 over x to the 5th. Right? And we know what that looks like, right? Kind of looks like 1 over x, except we have a much steeper sort of a corner here. But that's all that's going to be. All right. So, wow, that was a lot easier. So find the estimate the parameter, or eliminate the parameter to find the Cartesian. It's just going to, oh, and which direction does the arrow go in? See, that's always a good one. So how about we set if t is equal to 0, okay, then we get e to the 0, which is 1, and we get y to the 0, which is 1. So that was t equals 0. T equals 1, right? We get e to the t, so we get e and e to the negative 5. Okay, so we have e and e to the negative 5. So we start from here, and then we're getting e to this one. So it looks like our arrow is heading in that direction there. If I do t is equal to 2, we have e squared and e to the negative 10th. So we're way out here. Okay, so this arrow is coming down this way, right? So when they ask us about the arrows, I'm like, okay, I'm liking this. I think it goes to 0 pretty quickly, right? X to the negative 5, right? X gets pretty big, right? 2, we're at 1 over 32, so I don't like this one as much. I'm going to keep option B here as my choice. All right, match them. Are you kidding me? Like, all right. We have 4 matches, so I'm going to use process of elimination here, all right, to see what we can see. All right, check it out. This x, right, the x's here, they're all positive, right? Y's can be positive or negative, but in graph 3, my x's are all positive. All right, so in graph 3, x's are always positive. Y is, between, what's y between here? Y is between, looks like -1 and +1. Okay. So as I'm going to look at, like, what are my options? Okay. Notice, right, we have a t and an x here. We have a t on the horizontal. We have a y on the vertical. So my x's are always positive, right? My x's were always positive, and my y's range from -1 to positive. Aha! I think graph 3 matches with A. That's what they want you to do with this. Part 4, right? My x's are positive and negative, but my y's are always positive. Oh, look at that. All right. So those were the 2 hard ones. Okay, now we'll do the easy ones. All right. So look, my x's here. My x's go from -2 to +2. So do my y's. That's delightful. All right. My x's do this twice, right? They go from here to here, and they also go from here to here. So it's doing it 2 times. And y is only positive a little bit, right? Y is only positive for like between like -0.5 and 2. So let's see if we could find y is only positive sometimes. It's not very often. Yeah, I'm kind of liking this one. Okay. Kind of liking this one. So graph D is going to go with B. And then this first one, this is a very famous graph. We studied these in physics too, with the electricity. I don't remember what they're called. They do have a name though. I don't remember it, but they do have a name. And they were definitely, when x's and y's were both like trig functions like this. They're not matching really, but that's what this was. So I have some advanced knowledge to say, oh yeah, we played with them. I don't know, do you guys even do oscilloscopes anymore? We had to arrange an oscilloscope to do this. That's what we did in physics. But these had a name. It was a French guy. But they were both like sine waves to put together this way. So this one, like, because I have another class that kind of helped, we could do that. But you can also, like, okay, well, x's are positive and negative. X's go from 0 to 1. No, t's go from 0 to 1. X's go from -2 to +2. Y's go from -2 to +2. So when I'm looking at the y's here, right, we got to match. X's and y's are doing this. And it seems like they're equal, right? There's enough above the graph and enough below the graph. They're kind of the same. And that's the only one that's really following into that one. Okay, so I apologize that your calc class decided that if you had physics 2 lab, this would be a lot easier, but that's what they did. All right, what I'm going to do is I'm going to stop here and I'm going to do some more in another video here. Okay, so I will do more. What did we do? We did homework demonstrations up to number 7. Okay, so I'll follow up and I'll see you in a little bit.